Okay, so as Molly said, today's topic is on the Questa Verification IP. If you think about most FPGAs these days, customers doing a bunch of custom logic, but the I/O onto and off of the chip is generally through a bunch of standard protocols, whether it's PCIe or Ethernet or simple buses like SPI, or maybe from a hard drive, serial ATA. So a lot of times the data coming on and off the chip is through these standard interfaces. And, you know, it might even be that your custom interface is an AXI interface to that custom interface, so, or to your custom logic. So the question is, how do we get that data onto and off? Do you want to do full chip simulation, or if you're doing at just your block level, maybe you need some of these custom interfaces, and quite honestly, you don't want to spend the time to create a piece of verification IP that's going to send Ethernet traffic, certainly not PCIe traffic. So verification IP is one of the building blocks of our Questa verification platform. So that platform includes everything from the simulator, Questa Sim, our formal verification tools, our prototyping tools. How do you get the stimulus into these different engines? How do you manage and analyze all the results? And how do you do the debug? So Mentor has pieces for all these. Today we are focusing on the stimulus generation for these standard protocols. So, if you look at the history of things, these interfaces get more and more complex with every iteration. If you look at the, ARM buses, it started out in '95 with a fairly simple APV bus. That got more and more complicated, became the AHB bus eventually. Then you came up with the AXI buses, and and things just continue to get more and more complicated as we go along. If we look at PCI Express, in 2002 when PCIe first started, we were talking about a 2.5 gigabyte type interface. Those interfaces have gotten more and more and more complex to the point, in PCIe 4.0, we were at 16 gigabytes and our packet, and it's continued to get more complicated from there. Oftentimes these protocols have hundreds, if not thousands, of specifications, and trying to learn all of that so that you can send this data is just not something that you want to necessarily tackle. So what our Questa verification IP is it is a set of UVM agents. So in UVM terms, an agent is a piece of IP that can both monitor traffic on a bus and provide stimulus on that bus. Everything happens at a higher transaction level. We base that agent on a full test plan, so a full compliance test for whatever protocol we're talking about. From that compliance test, we build a set of coverage models, whether that be SystemVerilog cover points, cover directives, assertions, etc. So all of that coverage is built in. We also use that test plan to model creating a full set of sequences that can test that can do, as I said, a full compliance test on that protocol. As a user, you probably don't care about doing a compliance test. You probably trust that the piece of IP, the PCIe bus that you're using, controller, is meeting the specification. But by being able to do a full compliance test, that means we can send any sequence that your system is going to desire. You can also say, hey, we want to make sure that we can do these 10 different bus transactions. So you can use this coverage model to say, hey, let's make sure that these certain features are tested. All of the debug of the VIP happens at protocol level. So you get to put transactions in the wave window rather than having to stare at bit wiggles. And then there's full examples and documentation for every one of these protocols. So it really becomes a single place. If you have, say, a PCIe on your, if you've got a PCIe endpoint on your device, you can pick up our PCIe root complex VIP, drop it on, hook it up, generate all of your traffic, and do all the debug on that interface to make sure that things are working the way you intended, and you're getting data into the internal custom logic of your device. We do, like I say, include compliance tests with that. If for some reason you don't trust your IP vendors, IP, you can run a compliance test and make sure. Portable stimulus is kind of the newest verification methodology. We're not going to go into that a lot today, but we do support portable stimulus with all of our Questa VIP, and it just really helps you improve your productivity so you can quickly, get your test bench up and running and not worry about digging into the deep details of any protocol and start to test right away. So this right as of this summer is what the protocol library currently looks like. We sell this as these families. So if you acquire, if you buy the Ethernet VIP, the Ethernet VIP can take on all of these different types of Ethernet. If you buy the PCIe, you can go anywhere from PCI 2.1 up to the latest 5.0 standard. The serial interface line is, a lot of the simple serial buses like I2C and SPI and UARTs and things like that. The AMBA will give you basically all of the different buses for the ARM family. Display family will give you any of the different displays. So HDMI and DisplayPort are probably the two most common. The Mil-Aero family, SpaceWire and 1553B are probably the two most common in that military family. PCIe, as I said. We also have in green here, you see a couple of different memory families, 3 different memory families. So these allow you, if you have memory in your system, DRAM, say, you can pick it, by vendor. So, you can say, okay, we've got a Samsung KB224G, et cetera, part number. You pick out that part number, it will configure that piece of memory VIP to act as if it is that part number. So you can drop that down in your system for modeling memory. As I said before, all of the checking, all of the protocol, you have a full protocol compliance, and you have a set of assertions that are built in so that if traffic on your PCI bus starts to violate the PCIe protocol, you will get assertion warnings pop up, and it'll say, that this request flag was, not correct, or the different errors will pop up to show you. You can drop all of those assertions into the wave window for debugging what was wrong with it. When you drop an assertion into the wave window, that automatically drops all the signals involved with that assertion. So you'll get all the, bit level debugging as well as the transaction level debugging along with that. Each one of our VIPs is built off of a test plan for that particular protocol. So in this case, I'm showing the AHB test plan. So every feature of the AHB bus will be enumerated in the test plan. It will describe each different test that's being done. Then it has all the linkage to the included assertions, so that if you get an assertion failure on whatever, it will tell you that, this H-trans feature had some problem. You can come and look at that. This is good for one, just making sure that we had all the sequences required to send any transaction across that bus. But it also is good that you can kind of say, hey, we're going to be using, the feature of HWrite, the HBurst feature, whatever. You can go down and you can say, I need to collect coverage data on these different features because these are the things that are important to us. You can run your test bench, and at the end, you can look and say, okay, the features that we care about have been covered. We're feeling pretty good about that. So as I said, we start with that test plan. From that test plan, we build out a full set of sequences. Those sequences, we give you the API to say, I want to send this type of sequence. So as soon as you include that piece of IP in your test bench, you're given full documentation on that sequence. This is an example of kind of the transaction level debugging. So this is the visualizer wave window. You get the exact same with the traditional Questa debugger, that you can drop all of those transactions into the wave window, which basically what you see here is, on this AXI bus, I did a write to, channel 1 with these parameters here. Here I did a write to channel 0. There's another write. So you can kind of see, here's where maybe I did a read on some other channel. So you can drop those in. It's a lot easier, especially on these 2-wire buses like PCIe. You might have tens of thousands of cycles that make up a transaction. By having the monitor in there, so it can monitor the activity on that bus and turn it into, over this amount of time, a transaction with these parameters happened, is a hell of a lot easier to debug than trying to look at the 6,000 transactions on the 2-wire bus to figure things out. You also get a full ASCII text log of all transactions for each of these. So it'll tell you the time that it started, the time that it finished, and then what transaction happened on each of the buses. So for every VIP that you drop down, you're going to get a output transaction log. We've had a lot of customers use this successfully. So just a few things: Cypress, SD Electronics. They say they rely heavily on the verification IP for developing their own internal IP that you would give. ARM is another one. Microsemi used our verification IP to really flesh out their JTAG controller to make sure that it's doing everything correctly. On the PCIe front, most of the PCIe vendors, PLDA and Xilinx, Altera, et cetera, have all used our PCIe verification IP to help qualify their things. So just a few things. Not going to spend a whole lot of time on these case studies, but here's just a quote from folks at Microsemi. They said they had some really good results. Another one from Cypress, and then finally from ARM and PLD on PCIe. So anyway, we have, as I said, a complete compliance test. For most users, they don't really care about this because they assume that if they're using the Xilinx AMBA bus, that it's operating correctly. But sometimes you actually will find that things aren't necessarily working correctly. And by having these compliance tests, if you are seeing a problem, you can drill down into exactly what the problem is, and that helps you go back to Xilinx and say, hey, there's a problem with this bus. So these are all included with all the Questa VIP. This slide is just showing, if you look at the number of design engineers in blue at the bottom versus the number of verification engineers, you can see somewhere in the mid-2000s, in the mid-teens, the number of verification engineers actually started outweighing the number of design engineers on most ASIC projects. If you actually look at FPGA projects, we are actually finding it may not be number of engineers, but the amount of time that an engineer spends on an FPGA project has, started to wait to, they spend more time verifying than they actually do designing most projects. And so that just kind of goes to the fact that the verification problem has become the long pole in the tent. And by having some VIP for these complex protocols, that can reduce the amount of time that it takes to work on a project. So the verification IP is built on the UVM methodology. So at Mentor, we've got kind of, to get you to doing a full Testbench automation using UVM, we've had a few efforts over the last few years. So the first one is simplifying just getting a UVM environment up and running. To begin with, we created something called the UVM framework, which is a slightly simplified version of UVM and a UVM code generator that generates your test bench off some relatively simple templates versus writing all that code yourself. And that's kind of based on Questa Prime. Bringing up verification IP, our verification IP, we now have this thing called the QVIP configurator. That is a graphical tool that you say, hey, I need to do an ARM bus, and it brings up, a tablet and or a template, and you can kind of pick, okay, these are the address width, these are the different things, and then it generates all the code for that VIP. And it's really, we've had good response from the customers saying, hey, this makes bringing up this VIP much easier. And then finally, there is the Questa InFact for the portable stimulus that's there. So let's talk a little about this UVM framework and what it is, because in order to use the VIP, you do need to create a UVM environment. So if you're not familiar with UVM, creating that environment and creating, everything that goes into that can be a really daunting task, and it can take a while, especially if you're not, a UVM expert to start with. So with UVM framework, what we've tried to do is, shrink the time of getting your initial environment up and running and configuring your initial stimulus and getting you doing productive verification as quickly as possible. So what UVM framework really is it, at the heart of it, it is a UVM code generator, where we generate the UVM agents for any custom agents that you need to make. We facilitate bringing in the VIP into your UVM environment through the environment template, and it really gets you into a test bench, helps you avoid a lot of the pitfalls of making IP that's not reusable within your test bench, makes that test bench a little bit more correct by construction, and really jumpstarts you getting going as quick as possible. So if you look at a typical UVM environment, the base element of a UVM test bench is an agent. And what an agent does is it is going to, it kind of works hand in hand with this over this virtual environment with an interface. And it says, I'm going to monitor all traffic on this bus. I'm going to look at the bit wiggles on this bus, and I'm going to turn those back into, and it's going to say, when I see this activity on the bus, that means a read with this value happened. So this monitor BFM turns those bit wiggles back into transactions, hands those back up to the agent. The agent can use that to collect some coverage itself. It can feed that back over to a reference model, say. That reference model is saying, given this stimulus, I expect to see this out the other side. A scoreboard will say whether or not that, the received packet is what I expected. You might have a coverage collector in your environment. So you need to create all of this code. And it's fairly daunting if you look at it. Every one of these agents is probably about 15 to 24 files. The environment itself is probably 15 or so files. It becomes the thought of writing all that code yourself as a somewhat novice user is a fairly daunting task. So the UVM framework helps you with this template-based manner to create that code. So for every one of my agents, instead of needing to write those 15 different files for that agent, what I end up doing is creating a template. And that template, it says, okay, here's the IO for that thing. So it's, for this FPU, I've got input A and input B. I've got a result coming back. If you notice, this is from the Testbench point of view. So the two inputs into the floating point units are outputs of the Testbench. The result coming back is an input to the Testbench. I've got a start and a ready for that floating point unit. I probably should have an opcode port here that I haven't added yet. But anyway, I take this template, I hand it to the UVM code generator, and it outputs all of the code for that particular agent. It not only outputs all of the code for that, but it outlists the file lists for compiling and a make file to actually compile it. So in this previous example, I had two agents, I had an environment, and I had a test. So down here, I need to create a template for each of those agents. I need to create a template for my environment, and I need to create a template for a test. So, this was the first agent. I do that again for the second agent. It outputs all that. My environment, then, I describe that in a similar template. That outputs all of the code, and it outputs a make file, but that make file says, okay, I've instantiated this FPU thing, so it's going to call that FPU make file. So what actually comes out at the very end of here is you end up with a full test bench and a make file that's going to compile everything and get you up and running very quickly. The tasks you have left to do, because this is pulling a bunch of that boilerplate code, the tasks you have left to do in the UVM framework is that you need to go in and add your value added thing. You need to say, okay, when I get this task that says write data over this port, what is the signaling that needs to happen with that? So I need to go modify the driver right BFM to do that. I need to go modify the monitor BFM to say, when I see this activity, that's a transaction. You need to go in and put some constraints on your top level to modify what type of sequences are going to be sent, and then you need to extend the sequence base. So here's, say, the monitor BFM. It puts in this generic access task, and I go into that and I replace that maybe with a do read and a do write task. And I fill in what the signaling is to do a write and what the signaling is in to do a read. I do the same thing for the monitor, and then down here in the actual class, I've added a few constraints. So I need to put those constraints on just kind of to shape the type of data that's going to be generated. And, so that's creating my base environment. And then if I'm going to bring in VIP, I use my VIP configurator and I say like, okay, I need to put in an AMBA bus. It's going to have, an address width of 32, a data width of 32. Is it going to be a slave or a master? Is it going to have these different things? I go through and that generates the agent for that particular piece of VIP. You might need to put in like with the memory map, where does this piece of VIP live in the memory? As I said before, I'm configuring, width and is it a slave or a master? Is it acting for, etc. You then output all that code. And then when it outputs the code for that, it also outputs the string right here, which is basically the string that I'm going to include in my UVM environment to say, go ahead and all of the VIP that I've created, insert that as a sub-environment. So in this case, I went through the configurator, I created an environment that had a PCIe bus, a couple of AXI4, I guess 3 AXI4 buses, an APD bus. That got output as a sub-environment. I had the strings that I needed to include in my UVM framework. So here's a couple of the memory. Well, actually, I guess this is the rest of my environment. It's a predictor, a couple of other custom things that I put in there, and I'm up and running. So let's see. Example here. I've got this RTL in orange. I've got a few custom, a few VIP blocks that I'm going to put out. I can go through the configurator. I can go through my UVMF template generator. And basically, we had a customer who this is a customer design, and they basically said that, using this, they were able to get a test bench up and running for a fairly complex system within a couple of days. They had full transaction level debugging and were able to collect any of the coverage they needed for that. So we could really feel at Mentor we're the only EDA company right now that has the UVM framework for jumpstarting your UVM development. We have the VIP configurator for quickly configuring and including that VIP in your environment. We do full coverage collectors. We stimulus generation in the UVM world. If you want to, you can move up to portable stimulus and very quickly get running. So, we have everything for doing comprehensive protocol compliance testing, full featured VIP, UVM, Testbench Automation, and plenty of customers who are quite ready to attest to the quality there. So really, we have a large set of protocols, probably the most popular being PCIe, Ethernet, and AMBA probably being the next couple. We have this display family. We can do USB, a bunch of different protocols. It's all based on these UVM agents. The configurator helps to get things up and running rapidly. You can do full protocol compliance testing if needed. And this is supported in both simulation, in emulation, and actually we have formal protocols as well. So that's pretty much what I wanted to talk about on the VIP today. All right. Thanks, everyone.